Welcome to this problem-solving session. Today, we'll be tackling the problem titled Split a String in Balanced Strings. We'll explore how to approach this problem step by step and dive into different strategies to solve it effectively. Let's get started. In this problem, we are given a string S that contains only the characters L and R. A string is considered balanced if it has an equal number of L and R characters. The goal here is to split the string into as many balanced substrings as possible. Once you've split off a substring, it cannot be used again. The task is to determine the maximum number of balanced substrings that can be obtained. For the input, we are provided with a string S of length n, where n is between 1 and 10,000, and every character in S will always be either L or R. The output will be an integer representing the maximum number of such balanced substrings. For example, consider the input string RLRRLLRLRL. The output here is 4 because the string can be split into 4 balanced substrings, RL, RRLL, RL, and RL. Each of these substrings has an equal number of L and R characters. Therefore, the maximum number of balanced substrings we can achieve in this case is 4. Another example is the input RLLLRRRLR. Here, the output is 3. The string can be divided into 3 balanced substrings, RL, LLRR, and RL. Notice how the substrings are split sequentially, and once a substring is split off, it is not used again. Now, let's look at another example. If the input string is LLLRRRR, the output is 1. This is because the entire string is already balanced. It contains 4 L characters and 4 R characters, making it one balanced substring. Since there are no additional ways to split this string into smaller balanced substrings, the maximum number of balanced substrings is 1. This example demonstrates that sometimes the entire string itself forms the only balanced substring. The problem comes with certain constraints and guarantees. The length of the input string S is always between 1 and 10,000, and every character in S will be either L or R. Additionally, the problem guarantees that it is always possible to split the string into at least one balanced substring. This means we don't have to handle cases where no balanced substrings exist, as there will always be at least one valid solution. Let's consider some edge cases to better understand the problem. For the smallest possible input, such as RL or LR, the output will always be 1 since these strings are already balanced. If the entire string is balanced, like LLLRRR, the output will also be 1, as the whole string forms one balanced substring. For strings with alternating characters, such as RLRLRLRL, the output will be the length of the string divided by 2 because each pair of R and L forms a balanced substring. Finally, for inputs like RLLLRRL, the algorithm must correctly handle nested or overlapping unbalanced sections and split the string into balanced substrings wherever possible. To solve the problem of splitting a string into balanced substrings, we first considered the brute force approach. The intuition here is straightforward: split the string at every possible point and check if the resulting substrings are balanced. This involves iterating over the string to generate all potential substrings and then counting the occurrences of L and R in each one. If the counts are equal, the substring is identified as balanced, and we increment our count of balanced substrings. However, this method has significant drawbacks. The time complexity is O(n) squared, due to the nested iterations required for substring generation and validation, and the space complexity is O(n), to store these substrings temporarily. For large input strings, this approach becomes inefficient and impractical. To address these limitations, we explored an optimized solution using a single pass and a counter to track the balance dynamically. Instead of generating substrings, we modify a counter as we traverse the string, incrementing it 4L and decrementing it 4R. When the counter reaches 0, it signifies that the string is balanced, and we increment our balanced substring count. This optimization reduces the time complexity to O(n), as we only traverse the string once. The optimized approach also has a significant advantage in terms of space complexity, as it only uses a constant amount of extra space. There's no need for additional data structures to store substrings or perform validations. This makes the algorithm not only faster but also memory efficient. The key insight behind this approach is that a balanced substring occurs when the cumulative counts of L and R cancel each other out, which is precisely what the counter mechanism tracks. By directly working with the balance instead of explicitly splitting the string, we avoid unnecessary operations and streamline the solution. Because of its simplicity and efficiency, the optimized approach is the clear choice for solving this problem. It scales well for large inputs and is particularly suitable for competitive programming scenarios, where both speed and clarity of implementation are critical. When comparing the two approaches, the trade-offs become clear. The brute force method, while conceptually simple, quickly becomes computationally expensive for longer strings, especially those close to the problem's upper limit of 10 to the power of 4 characters. It also demands more memory, which can be a challenge in resource-constrained environments. On the other hand, the optimized approach is not only faster due to its time complexity but also space efficient, requiring no additional storage beyond a few variables. From an implementation perspective, the optimized approach is cleaner and less prone to errors, as it avoids the complexity and redundancy of nested loops and manual substring checks. Overall, the optimized approach strikes the best balance between performance, memory usage, and ease of implementation, making it the most practical and robust solution for this problem. In this problem, we are tasked with splitting a given string into the maximum number of balanced substrings. A balanced substring is defined as one containing an equal number of L and R characters. Instead of testing all possible substrings, which would be inefficient, we use a greedy approach. This method allows us to identify balanced substrings as we process the string in a single pass. The key idea is to maintain a running count of L and R characters using a variable called balance. Every time the balance variable returns to 0, it indicates that we found a balanced substring. To track the total number of these substrings, we use another variable, count. By iterating through the string and updating these variables, we can efficiently compute the result. As we process each character in the string, we update the balance variable by incrementing it for an L and decrementing it for an R. Whenever balance equals 0, it means we've encountered a balanced substring, so we increment the count variable. This approach ensures that we split the string at the earliest opportunity to maximize the number of balanced substrings, which perfectly aligns with the problem's requirements. The greedy method works because it prioritizes immediate, locally optimal splits, which also lead to the globally optimal solution. By avoiding the need to evaluate all possible substrings, we achieve high efficiency, using only a single pass through the string. This makes the solution both time and space efficient. With just two integer variables, balance and count, we keep the implementation simple and memory usage minimal. The efficiency of this algorithm is evident in its complexity analysis. The time complexity is O(n), where n is the length of the string, since each character is processed exactly once. The space complexity is O(1), as we only use a few integer variables to track the counts, without storing intermediate results or substrings. Additionally, the algorithm handles several edge cases gracefully. For example, if the input string is empty, the output should be 0 because there are no characters to process. If all characters in the string are the same, like LLLL or RRRR, no balanced substrings can be formed, so the output remains 0. For strings that are already balanced, such as LLRR, the algorithm correctly identifies this as one balanced substring. By splitting at every point where balance equals 0, it ensures that nested balanced substrings are not double counted, providing an accurate result. To see the algorithm in action, consider the input string RLRRLLRLRL. We start with balance and count both initialized to 0. Processing the first character R decreases balance to -1. When we encounter L, balance returns to 0, indicating a balanced substring, so we increment count to 1. The same process continues, 2 R characters decrease balance to -2, and 2 L characters bring it back to 0, forming another balanced substring and increasing count to 2. This process repeats for the remaining characters, identifying 2 more balanced substrings and incrementing count to 4. By the end of the string, the algorithm returns the total count of balanced substrings, which is 4. This example highlights the simplicity and efficiency of the approach, as it processes the string in a single pass and uses only integer counters. Finally, the code implementation of this algorithm is straightforward. We define a function balanced_string_split that takes the input string as its parameter. Inside the function, we initialize balance and count to 0. We then iterate through each character in the string, updating the balance variable based on whether the character is L or R. Whenever balance equals 0, we increment count to reflect the discovery of a balanced substring. After processing all characters, the function returns the count as the final result. For example, calling balanced_string_split with the input RLRRLLRLRL outputs 4, which matches the result from our earlier walkthrough. This concise implementation is both efficient and easy to understand, making it a robust solution for the problem. This Python implementation solves LeetCode problem number 1221, split a string in balanced strings using a greedy approach. The problem requires us to split the input string into the maximum number of balanced substrings, where each substring contains an equal number of L and R characters. The function balancedStringSplit takes a string S as input. It initializes two variables, balance to keep track of the difference between the counts of L and R characters, and count to store the number of balanced substrings found. The function iterates through each character in the string S. If the character is L, it increments the balance by 1, and if the character is R, it decrements the balance by 1. This way, the balance variable reflects whether we have an excess of L characters, positive balance, or R characters, negative balance. Whenever the balance becomes 0, it indicates that we have found a balanced substring. At this point, the count variable is increment by 1. Finally, after traversing the entire string, the function returns the value of count, which represents the maximum number of balanced substrings that can be obtained from the input string. This approach is efficient with a time complexity of O, n, where n is the length of the string, as it involves a single pass through the string. The space complexity is O, 1, as no additional data structures are used to store intermediate results. This is the Java implementation of LeetCode problem number 1221, split a string in balanced strings. The code mirrors the Python logic, with minor adaptations for Java syntax. The method balancedStringSplit takes a string input and counts the number of balanced substrings, where the number of L and R characters are equal. Key differences include explicit type declarations, use of char arrays for iteration, and Java class structure. The algorithm runs in O, n, time complexity, as it processes the string in a single pass. To solve this problem, we aim to split the string into balanced substrings, where the number of R and L characters are equal. Starting with the input S equals RLRRLLRLRL, we initialize two variables, balance to 0, which tracks the difference between R and L, and count to 0, which records the number of balanced substrings found. First, we process the character R. Since it's an R, we decrease balance by 1, making it -1. At this point, balance is not 0, so no balanced substring is identified yet. Next, we process the second character L. This time, because it's an L, we increase balance by 1, bringing it back to 0. A balance of 0 means we've found a balanced substring, so we increment count by 1. Now count equals 1. Continuing with the next three characters, we process R, which decreases balance to -1, another R which decreases it further to -2, and then L, which increases it back to -1. Since balance is still not 0 after processing these characters, no additional balanced substring has been found yet. Now, we process the fifth character, another L. This increases balance by 1, making it 0, which indicates we found another balanced substring. We increment count again, so now count equals 2. Moving forward, we process the remaining sequence of characters, R, L, R, and L. For R, we decrease balance to -1. For L, we increase it back to 0, identifying another balanced substring and incrementing count to 3. Then for R, we decrease balance to -1 again, and finally, for L, we bring balance back to 0. This gives us yet another balanced substring, so we increment count to 4. At the end of this process, the string has been split into 4 balanced substrings, RL, RRLL, RL, and RL. The final output for this example is count equals 4. In the second example, we analyze the input S equals RLLLRRRRR. Once again, we initialize balance to 0 and count to 0 to begin tracking our progress. First, we process the sequence of characters R, L, 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 and L. For R, we reduce balance to -1. For the first L, we increase balance to 0, which indicates a balanced substring, so we increment count to 1. Processing the next 3 L characters, we increment balance successively to 1, 2, and 3. Since balance is not 0, no additional balanced substring is found at this stage. Next, we process the sequence R, L, and R. For each of the first three R characters, balance decreases from 3 to 2, 1, and finally 0. At this point, we identify another balanced substring and increment count to 2. Then, L increases balance to 1, and the final R decreases it back to 0, marking one more balanced substring. We increment count to 3. By the end, the string splits into 3 balanced substrings, RL, LLLRRR, and LR. The final output is count equals 3. As a final example, we examine the input S equals LLLRRR. Starting with balance equals 0 and count equals 0, we process the first 4 characters, all L. For each L, we increment balance by 1, resulting in values of 1, 2, 3, and finally 4. Since balance remains non-zero, no balanced substring has been found so far. Next, we process the remaining 4 characters, all R. For each R, we decrease balance by 1, bringing it down successively to 3, 2, 1, and finally 0. At this point, balance equals 0, indicating a balanced substring that spans the entire string. We increment count to 1. Since there are no more characters left to process, the string splits into just one balanced substring, LLLRRR. The final output is count equals 1. The time complexity of this solution is O, n, where n represents the length of the input string. This is because the algorithm processes the string in a single pass. Specifically, it iterates through each character using a for loop, performing a constant amount of work for each character. For example, during each iteration, the algorithm updates the balance variable and checks whether its value has reached 0. These are simple operations that do not involve any nested loops or additional traversals. As a result, the total number of operations scales linearly with the size of the string. Additionally, all operations inside the loop, such as if conditions and variable updates, are constant time operations, meaning they take the same amount of time regardless of the input size. Therefore, the linear traversal dominates, giving us an overall time complexity of O, n. The space complexity of this solution is O, 1, meaning the algorithm uses a constant amount of additional memory regardless of the input size. This is due to the fact that only 2 auxiliary variables are maintained throughout the execution, balance and count. The balance variable tracks the difference between the number of L and R characters as the string is traversed, while the count variable keeps track of the number of balanced substrings found. Since these variables are integers, they occupy a fixed amount of memory. Furthermore, the input string is passed as an argument to the function and is neither modified nor duplicated, so no additional memory is required for storage. As there are no dynamic data structures like arrays or hash maps that grow with the input size, the space usage remains constant, making the space complexity O, 1. The algorithm's performance remains consistent across all cases because it always processes the input string in a single pass. In the best-case scenario, such as when the string is perfectly balanced with alternating L and R characters, the algorithm still requires O, n, time to traverse the string. Similarly, in the worst-case scenario, even if the string is heavily unbalanced, the algorithm continues to perform a full traversal, resulting in the same O, n, time complexity. On average, the algorithm behaves the same way, as the linear traversal of the string is always necessary regardless of its composition. When compared to a brute force or naive approach, the efficiency of this solution becomes more evident. A brute force method would involve generating all possible substrings of the input and checking each one for balance, which could lead to a time complexity of O, n cubed, and a space complexity of O, n squared, due to the storage of intermediate results. By contrast, this optimized solution achieves a significant reduction in both time and space complexity, down to O, n, and O, 1, respectively. To mathematically prove the big O complexity, let the length of the string be n. During the single pass through the string, the algorithm performs a constant number of operations for each character. These operations, such as updating the balance variable or checking a condition, are O, 1. Since there are n characters in the string, the total number of operations is n multiplied by O, 1, which simplifies to O, n. Regarding space complexity, the algorithm uses only 2 integer variables, balance and count, which require a fixed amount of memory regardless of the input size. No additional space is allocated for data structures that grow with the input. Therefore, the auxiliary space usage remains constant, resulting in a space complexity of O(1). This confirms that the solution has an asymptotic time complexity of O(n) and a space complexity of O(1). When solving this problem, there are several common pitfalls to watch out for. One major mistake is not accounting for edge cases, such as empty strings, strings with all identical characters, or strings that don't contain any valid substrings. These edge cases can lead to incorrect results or even runtime errors if they're not handled explicitly in your code. Another error is inefficient substring validation, like repeatedly checking the same substring multiple times. This redundancy can significantly increase the time complexity, sometimes to O(n cubed), or worse, making your solution impractical for larger inputs. Additionally, mistakes in designing sliding window or pointer logic are frequent. For example, forgetting to shrink the window or mismanaging pointer adjustments can lead to infinite loops or missing certain substrings entirely. Lastly, it's easy to confuse the problem's definition of balanced with simply having equal frequencies of characters. Remember, for this problem, balanced refers specifically to equal counts of L and R, so it's crucial to align your logic with the exact problem requirements. Now, another common oversight is ignoring constraints or optimization hints provided in the problem statement. For instance, if the string length can go up to 10 to the power of 4, attempting a brute force solution that checks all substrings will likely result in a time limit exceeded error. Instead, you should aim for more efficient algorithms. Speaking of efficiency, recognizing patterns is key when solving balanced substring problems. Many of these involve tracking counts or differences, like maintaining a balance factor or character frequencies. You should also decide whether sliding window or prefix sums are more suitable for the task. Sliding window techniques are better for contiguous substrings, while prefix sums excel at cumulative comparisons. Always ensure you understand how balanced is defined in the problem, as variations in this definition can significantly impact your approach. Lastly, after implementing your solution, rigorously test it on edge cases, such as strings of minimum or maximum lengths, strings with all identical characters, or strings without any valid substrings. This helps ensure robustness and correctness. This problem also shares similarities with other problems on LeetCode, and recognizing these relationships can help you refine your approach. For instance, LeetCode 1221 focuses on splitting a string into substrings where L and R are balanced, making it a direct application of balance tracking. LeetCode 1248, on the other hand, involves counting subarrays with a specific property and highlights the importance of sliding window and prefix sum techniques. Another related problem, LeetCode 76, deals with finding the minimum window substring that meets certain constraints, making it a classic example of sliding window logic. Finally, LeetCode 424 challenges you to maintain a balanced substring while performing operations to maximize its length. By studying these related problems, you can deepen your understanding of common patterns and techniques, such as balancing character counts, managing pointers, and optimizing for performance. When approaching problems like this, it's also helpful to consider alternative strategies and weigh their trade-offs. For example, brute force substring checking is straightforward to implement but highly inefficient, often running in O(n cubed). This approach is only practical for small input sizes or as a starting point for optimization. Sliding window techniques, on the other hand, are highly efficient with a time complexity of O(n), but they require careful management of pointers to avoid errors. Prefix sums or hash maps are another powerful option, especially for problems involving cumulative balances or range queries. However, they may require additional space, so you need to account for memory constraints. Lastly, two-pass solutions offer simpler logic and can be easier to implement, but they may double the runtime, typically resulting in O(n). These are best used when clarity and simplicity are more important than achieving the absolute best efficiency. By understanding these trade-offs, you can choose the most appropriate approach for the problem at hand and the constraints you're working with. Great job! In this session, we tackled the problem split a string in balanced strings. We discussed the brute force approach and its applications. Remember to practice similar problems to strengthen your skills. Thank you for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!